space. The general case rotation about any arbitrary space happens often in robotic animation simulation. This is very common. All the previous discussion, rotation by any arbitrary axis in space are accomplished by this procedure using translations and simple rotation of the major axes. Just the K8 rotation of when the axis is done, then the line procedure is to make this arbitrary rotation like this is one of the major axes. So assuming arbitrary axis is space through the point, remember the 2 points, right? So if you know the anchor points, you assume there's an anchor point, and it could be origin, and then you know the position from that, x0, y0, z0, and from that on we find the vector, and from the vector, unit vector, we define the direction cosines, which is the mapping corresponding to the components of that unit vector. So rotation about this axis by some, and then you say, well, I'm going to rotate around by, say, delta, and then this is following the procedure. So that's the same thing we did in our textbook. So translating, so translating this this object to the origin, perform a proper rotation, rotating at a zig, and then come on back. So in general, making arbitrary axis passing through the origin coincidence one of the coordinates to make require 2 rotations about the other 2 axes. We want to rotate by z. We're going to first rotate through the other 2, so, x or y. To make the arbitrary rotation axis coincident with the z, we make through x and then y. That's the normal procedure that you take. To determine the rotation angle alpha, the x-axis is in place, so we do this the same thing, finding the d using the component of that one, and then through that component over this d, the length of that projectile to that plane, we find a cosine alpha or sine alpha. And then going to the other plane, we need to another angle, and then it's beta is related d and the cosine cx. Right? And so he actually simplified all that. He just bypassed all the derivation. He showed you the, and then he put all this together. Now remember, we're doing a pre-multiply. These notations in this book is always post-multiply. So we're pre-multiply. He's, because he write the other way, so he's doing the P, then the T, and the D prime. So the order, we go from here to here. This one first is a concatenation of just, here's this the other way. So the sequence of many different concatenations, we start from here to there. So you can do this translation back, rotation x, rotation y, rotation delta, rotation y, inverse rotation x, and inverse translation. Okay? And he put in the t here, the rx here, the same thing as we had before, just different derivation. X, this is the one we saw before. The figure he showed is the same thing. Take this axis, so z is up. So I want to locate this to this xz plane. And so to that, this projected onto here to give you this d here. And then next one you rotate around y. But y positive goes this way, and he's going the other way. The same derivation, the same thing. You go to ry, comes dd, and then r. Now you notice that the sign here is flipped because this is a pre-multiply, no, post-multiply. Okay? rotating around delta, around z, this is 1, and this is the angle rotate, and doing the reverse. Okay, nothing new, it's exactly the same thing. So here's the problem. He uses this problem throughout his book, which I think is useful to see. I want to point out a few things. When you write on paper, right, the geometry, right, this point, vertex, P, right? So P is represented by, so how do you represent P? The first question to you. P is what's P?
Oh.
So isn't just like
P1
x
minus
coordinate?
P0? Or no, that's
Whatever, I mean P0, you call P0, P1, P1, whatever you get. So when I write it in vector form, what's that?
oh, so you got X, Y, Z, or
Yeah, so you have like px, py, pz.
X, Y, Z. 1. Okay, so if you're missing 1, you're gonna miss point. Because the T is a 4x4, you cannot have a P which is 1x3 or 3x1, right? Okay. And now you have to have 1. So now we see. So you see this angle, his object, he defines his object a cube, simple cube. So he has a cube here. Cube, right? Cube. And he come here and say, well, I'm going to cut one piece off. But this part is gone. So he has this flat side. But anyway, this point is still kind of fictitiously still there, right? And if you cut it equal distance here, the diagonal actually still come out from here, like this one. So this orientation is actually normal to this plane. Okay? That's just for the sake of explaining what he's doing. And then he called this, he uses P, X, the A, B, C, D. What is this? Now he has to give, so every time you model your objects, right, you define the points. So now he has several points. How many points? Originally he has 8 points. Right? Now he has 8 minus 7, 8, 9, 10. He has 10 points. So his object here is a cube without the corner, right? And it would be either, so if we show column-wise, right, I would have A, B, C, D, this one is probably A, B, C, D, and then he said F, G, H, I, okay? So he has A, B, C, D, and I. And each one has this one coordinates, right? The rest would be X, Y, Z. Okay? So when you define your model, that's what I expect to see. Number of points, then the coordinates. But he's doing the other way, right? He's the other way. He's writing row column. So he has this vector this way, and then he has A, B, C, I, and X, A, Y, A, C, A, 1, right? So this is the number. So A is at 212, B is 312, and so forth. Okay? You get this object. Now, the point here is saying, I want to rotate, because this object is not, just like in our case, your door is not aligned with the major axis, when you move around the door, you cannot just rotate the object around this axis. And then he purposely cut a corner such that this axis rotation is not on the major axis. Okay? So what does he do? So what you do is pick this point, or F, originally F actually. Right? Pick this original F, even though this is off. You take this one and then you can connect to the other side. Now you know the orientation of this axis that he's rotating around. Okay. That's his problem. His problem is, well, I want to rotate around this angle, and going around this way. So what he does here is he take this axis and he want to match this one with the Z. So he has to rotate it, move this one here, and rotate it such that this one becomes part of the Z. Z sticking out from the book page. Now we know the formula. Now you just compute. I just want to show you the numbers. So I can go up a little bit for you to see. So the first thing is determine the orientation of that vector and define its direction cosines. And so that's what you compute. Right, so you need to know how to compute a vector, position vector. Given position vector, given numerical. And then once you have Cx, Cy, Cz, and then you can compute a D. Once you can compute a D, you can compute the cosine alpha and the direction cosines. And for that one, you can plug all these numbers in. Once you have the numbers, you can plug into the transformation matrix. The T, the Rx, the rotation on Y, and then rotation around the delta, and then reverse back. So now you have the numbers to do the rotations. But it's not that difficult. The only difficulty is to visualize what you want to do in terms of how you're going to